So what is mathematical induction? Well, simply, it's just a proof technique. It's a way to prove something about a set. It's used to prove universal properties. A universal property is something that's true for every element in a set. For example, if I have like the set of all dogs, and I want to say all dogs have tails. That's a universal property. It's something that I want to show is true for everything in my set. Thirdly, mathematical induction is used on well-ordered sets. This can be, I guess, vaguely explained as just a set with some type of order. It always has a least element and then an element after that. So first, second, third, and so forth is something that you would see in a well-ordered set. Everything has a position and there is always a least element. You might be thinking, why can't we just use exhaustion to prove a universal property? Why can't I just go through every single element in my set one at a time and show that the property holds? Well, this will only work really with finite sets. Like if I have a set of buttons and I want to show you that all of my buttons are pink, I can go through each button and show you that it's pink, but I can't do this with an infinite set of buttons. I will never have enough time to show you that every single one is pink. So we have to turn to a different proving method than exhaustion, and that's where induction comes in. So the classic representation of mathematical induction is dominoes. This is probably the best intuitive way to explain what's going on in mathematical induction. So if I want to prove to you the property that all dominoes fall, or that all dominoes in my set of dominoes have fallen, there's really only two things I need to show you. So if I have this string of infinite dominoes, I can't go through every single one and show you that it has fallen, but there's two things that I have to know in order to believe that all of these dominoes will fall. Let's say I pick a random domino. I'm going to call it K, but it can represent any number in my set of dominoes. And I know that if K falls, so will K plus 1. If K falls, so will the next number in front of it. That means that no matter what domino I knock down, the next one will, and then the next one will. But this doesn't prove automatically that all my dominoes fall, because I don't know that K has fallen. The last thing I need to know in order to know that all my dominoes will fall is that the first element falls. If number 1 falls, and I also know that for any K that falls, the next one falls also, then I know that all of my dominoes will fall, because 1 will knock down 2, which will knock down 3, which will knock down the rest of the dominoes in order. So I don't have to look at every single domino. I just need to know that K knocks down K plus 1, and that 1 has been knocked down. Then all of my dominoes will fall. This is the idea of mathematical induction. Okay, so let's do an example. Instead of dominoes, I'm going to be looking at the set of natural numbers. And instead of the property all dominoes fall, I'm going to look at the property that n is less than 2 to the n for all n. And I'm going to see if I can show this through induction. So remember the two things I need to show. I need to show that this is true for the first element in my set, and I need to show that if it's true for some arbitrary k, then it will also be true for k plus 1. So my base case is showing that it's true for the first element. This is pretty obvious because since we know 1 is less than 2, then obviously 1 is less than 2 raised to the 1. So we're done here with my base case. Now it's time for the inductive hypothesis. This is where we suppose it's true for k. So I'm going to suppose that k is less than 2 to the k for some natural number k, and I want to show that this is also true for k plus 1. Note that 1 is less than 2 to the k. This is going to be important in my proof. Alright, so if k is less than 2 to the k, then I can add 1 on the left, and I can add 2 to the k on the right, and my inequality will still hold since we noted that 1 is less than 2 to the k. And from here, all we really need to do is simplify. If I simplify the right, I get 2 times 2 to the k, which is greater than k plus 1. And I can simplify that further to 2 to the k plus 1. And there we have it. K plus 1 is less than 2 to the k plus 1. So I've just shown through induction that this property is true for all n, because it's true for the base case, and if it's true for k, it must also be true for k plus 1. Therefore, this is true for all of the elements in the natural numbers. So my final statement is n is less than 2 to the n for all n by mathematical induction. Alright, thank you for watching.